Hello viewers, welcome back to our series of lectures on the topic electromagnetic spectrum. In this series, we have so far talked about UV visible spectroscopy, and we'll continue the discussion on the same, and today we will take up Woodward-Fizzer rules for INOs. It's a continuation of the previous session wherein we talked about the Woodward rules for dienes and all. The session is planned as follows, that is, to begin with, we will briefly review the contents of the previous sessions. Thereafter, we will come down to the main theme of today's session, that is Woodward-Fizzer rules for INOs. To talk about this, we will first establish the basis for these rules, and then thereafter we will state the rules and see the application of these rules for INOs. And towards the end, we will sum up what we do in today's session. Now, let's recall what we've done so far. What we've done so far is we started by explaining the origin of UV visible spectrum and outlined its significance. Thereafter, we outlined what are the characteristics of a UV visible spectrum, and then what are the factors which affect them. That means the characteristics being the intensity, the position of the band and the width of the band, and the factors which affect them. And then thereafter, in continuation of talking about the factors, we took up the concept of color and related it to the conjugation in the molecule. It was done in a very elaborate way. Having done that, we moved on to explaining the principles of spectrophotometer, that is the device which is used for measuring the measurement of UV visible spectrum, and spectrophotometry. Spectrophotometry basically is an application of UV visible spectrum. And then we took up certain important applications of spectrophotometry. Then in the previous session, we focused our attention on to stating what are the Woodward-Fizzer rules for dienes and discussed their application on a wide variety of molecules over there. Okay, so that is what we've done so far. Now let's move on to today's session. The basic theme for today's session, as I mentioned earlier, is Woodward-Fizzer rules for INOs. We'll start by establishing what is the basis for these rules over there, and what kind of rules are there, and then we'll come down to the applications part of it. Okay, so as regards the basis, basically we start by talking the basic chromophore, that is the carbonyl chromophore. In case of carbonyl chromophore, we have learned in one of the earlier sessions that the energy level diagram for carbonyl chromophore is as follows, wherein we have got sigma, pi, n, pi star and sigma star. These are different energy levels, and this is the kind of arrangement of energy levels in the order of increasing energy. Now, if I look at a typical chromophore of this kind, typically what we have is the sigma orbitals are filled, so are pi, and even non-bonding electrons are there. This orbital also is filled. And the possible transitions in this case are of two types. One is the pi to pi star transition. That means we start the molecule the molecular orbital pi to pi star, the transition takes place, and this is observed somewhere around 195 nanometer. This is an allowed transition, but it occurs outside the range of the UV visible spectrum. And the second transition happens to be that n to pi star transition. That is, this transition, since it is of low energy, this is observed at higher wavelength. This is observed in the UV visible range, but it happens to be a forbidden transition. That's why we observe it, but as a weak band over there. So that is typically the spectrum what you observe in case of carbonyl chromophore, because that is the basic chromophore in case of INOs, the starting point of it. Now, if you go further and look at this basic chromophore of carbonyl, we find that if I have different substituents which are put onto this carbonyl chromophore, we find that the absorption maxima is affected significantly. Let's take some examples there. This is typical aldehyde, about 293 nanometers, and then if I just substitute this hydrogen by a methyl group, it comes to 279, and so on and so forth. A halogen over there, this takes it further down. Or if we have NH2, it is 214. If it is an OH, it is 204, and so on and so forth. So what you find is that this basic chromophore, if the number of substituents are there on this chromophore, so they affect the energies, the energy level diagram for this carbonyl group, and as a consequence, we find that the lambda max position for this carbonyl, the transitions there, the n to pi star and pi to pi star transition, so they shift either bathochromically or hypsochromically. Now, but since our objective is to talk about enones, so basically enone is a combined kind of a chromophore, where there is an ene, there is an one. So what we talked so far is about an one, that is a ketone. Now, if we have got a conjugation, that means if we have got a carbonyl compound which is in conjugation with an ene, what we get is an enone. So what happens in such a case? This is my molecule which is acetone, a ketone here. But if this ketone, this carbonyl chromophore out of this happens to be in conjugation with a double bond over there. So this forms what is called as an enone, enone. In this case, what you have is, this is the kind of energy level diagram what we have here. That is, when there is a conjugation, we find that the basic energy level diagram remains the same. But what happens is, because of this conjugation, we find that this energy level, this pi, this becomes slightly of higher energy here in case of enone, and this pi star becomes of lower energy, whereas non-bonding n orbital remains of the similar energy as it is in this case over here. So as a consequence, what happens is, the energies of both these transitions, say pi to pi star was from here to here. Now since this level has become stabler, energy has decreased here, for this level energy is increased. So this transition will be of low energy. Low energy means it will go to higher wavelength. We find that it is observed around 203 nanometers there. It is come in the UV visible range. Whereas this transition here, this n to pi star also is shifted, because this also is of lower energy as compared to this one, but this shift is smaller, because in this case only one energy level has become of lesser energy. In this case, both energies, the energies of both the levels were kind of altered over there. As a consequence, what happens is, we find that is both the transitions, that is n to pi star as well as pi to pi star, they move to higher wavelengths. There is a bathochromic shift there because of the energy being decreased over there. Okay. Now, so that is the way the conjugation comes in there. So that's the transition there. And then what we have is, we have seen earlier that different substituents on this chromophore also affects the location of the band over there. So these two things form the basis of the so-called our Fischer Woodward Fischer rules here. What you have to take note of here is, that is, the effect is more pronounced for pi to pi star transition there, and whereas it is so very pronounced that if there is an extensive conjugation in the molecule, what can happen is, this pi to pi star transition may go even beyond n to pi star transition. As typically, if you remember, we mentioned that in a carbonyl chromophore, there are two transitions there. One is pi to pi star, which is typically little less than 200 nanometers, and n to pi star, which is beyond 200 nanometers, but that is a weak transition. But if there is an extension of conjugation, this pi to pi star transition can even go beyond. There can be so much of bathochromic shift that it goes beyond the n to pi star transition, and that is a typical thing what we make observations of, because the pi to pi transition is the allowed transition. So typically these Woodward Fischer rules, which we are going to now take up, they are more relevant for the pi to pi star transition rather than n to pi star transition there. Okay. Now let us see what are these rules here. Now, if you remember, in the previous session we talked about the rules for dienes there. In there, what we did was, we defined what is the base chromophore and what is the base value for that, that is the lambda max value for that. In this case also, we continue in the same direction, and what you find is, for in case of enones, there are different kind of chromophores have been identified there. If we have got acyclic enone like this, we have a carbonyl there, and what you have is a conjugation there. The base value for this is given as 215 nanometers there. But if you have a chromophore of this kind, that means part of the chromophore happens to be a part of a 6-membered ring, then this is having a value of again 215 nanometer. That means the ring doesn't affect the lambda max position over there. But if I got a 5-membered ring here, we find that the value happens to be 202 nanometers. That is, there's a decrease in the value there. And if you got acyclic dienone, that means that suppose there is a conjugation there. You have, this is my chromophore on here. This is first conjugation. This is second conjugation. So in this case, what happens is, the value happens to be 245 nanometers, which can be rationalized as the base value of 215 plus about 30 nanometers as a kind of contribution of the conjugation here. So that is how it is given as 245 nanometers. So typically when we talk about using these rules, we find that we have to first identify what is the kind of enone, the type of enone we have, and accordingly we'll ascribe a base value to that. So that is the first step. Thereafter, the second component we have is the contribution of substituents. This is much more elaborate as against what we had in case of dienes there. This goes as follows. So these are different possible substituents we have here, and it's important to note here that is the position of the substituent also matters in this case, and this is the respective contribution here. So how do we read this table is, this is extension of conjugation as we had before, it's about 30 nanometers. We add 30 nanometers to the base value to get the contribution of conjugation. Now if you got an alkyl group or a ring residue, we find that it also contributes, and what you see is this is alpha, beta, gamma and higher. What that means is, if it is at alpha position, the contribution is about 10 nanometers. At beta position, it is 12 nanometers. At gamma, it is 18, or even beyond gamma, delta, omega, etc. For all such positions, it will be 18 nanometers each. Similarly, for an OH, we find that alpha, beta, gamma and higher, we have got 35, 30, 18 and so on and so forth. So this is an exhaustive table here, which with little use we will get used to it. That is, for an OR, this is alpha, beta, gamma, delta. So these are the corresponding contributions of these substituents to the lambda max position there. And two more things you have to take note of here is, that is, we had the similar thing in case of dienes also. That is, our exocyclic double bond gives me a contribution of 5 units, but this is very, very significant here. That is, if we have a chromophore in such a way that there is a homocyclic diene component which is in conjugation with our the basic chromophore, that is enone, then there is a plus 39 nanometer contribution, which is very, very significant. We'll take some examples of this as well. And I'm sure that from the previous session you understand what is the meaning of an alkyl group, what is the meaning of a ring residue. We also understand what is the meaning of an exocyclic double bond. We will not repeat all that there. We assume that we know about it. In case you have any doubts, you can go back to the previous session and try to clarify for yourself the meaning of these terms, alkyl group, ring residue and so on and so forth. We will be using them, probably it will be refreshed as we move further. Before we go further, one more point which probably is very, very significant here is, that is the base values and the contribution of substituents, as mentioned in the two kind of slides we discussed here. They basically talk about, they predict the value of for the lambda max for a given system for the solvent to be as ethanol or methanol. So that is the kind of, because as you remember, the basic premise or basic, because these rules are very, very empirical, and the rationale comes from here is, that is Woodward and Fischer, what they did was they studied the UV spectrum of wide variety of molecules, and from there they empirically worked out, that is what is the contribution of a base chromophore and what is the contribution of different substituents there, and most of the data was in the alcoholic solvents there. So all these values pertain to ethanol as a solvent. But suppose I make a measurement in a different solvent, then I have to bring in the contribution of solvent also. There is something called as solvent correction there. Incidentally, for dienes we didn't have any solvent correction because the contribution solvent was not significant, but in this case the contribution is significant here. And how do we go about is that firstly we compute expected lambda max value for ethanol as a solvent on the basis of the previous two things, that is the base values and the effect of substituents there. Having done that, the third component happens to be our solvent correction. So we apply that and we get the value of lambda max for a given solvent. We'll take one example for this as well. So as per Woodward-Fischer rules for enones, what we have is the lambda max for a given molecule, a given compound, will be made up of three components there. First, the base value of the chromophore, that is whether it's a acyclic, enone or whatever, and then we will have some of the contribution of all the substituents over there. So we will see what is the substitution, what is the location, and add the contribution accordingly, and then we apply the solvent correction. So these three components constitute to give the predicted value or the calculated value for lambda max for a given molecule. Okay, now we are equipped to take up certain examples, the application of these rules here. Let's take the first example here. This is a simple molecule here, acetyl oxide. Now in this case, what we see is this is my carbonyl here and this is ene. So this is enone, this is my basic chromophore here. So for this is acyclic chromophore. So the base value happens to be 215 nanometers there. Then what do we have is, so since this is my chromophore, on this chromophore there are only two substituents there. This is one methyl here, another methyl here. So this basically are two alkyl substituents. And this alkyl substituent now is very, very important to understand here. That is, now if I have got this as my chromophore, that is, this is my carbonyl, this is ene here. So from the carbonyl we start. So this is my alpha position, this is the beta position. If there's extension over there, we got a gamma, delta, and so on and so forth. So we should be clear about what is the meaning of alpha, beta, gamma, delta, and so on and so forth. They basically pertain to the carbon atoms starting from the carbon next to the carbonyl group there. So this is my alpha position, this is my beta position. So in this case, there are two alkyl substituents at beta position, and we know from the table that each beta alkyl substituent contributes about 12 nanometers. So these two will add together. So 2 into 12 will give me 24 nanometers, and the two will add together to give me a calculated value of about 239 nanometers. So that's how I use these rules over there, and the observed value happens to be 237 nanometer, which is in fair agreement with the calculated value over there. Okay, now let's move further. Take another example. Now in this molecule, again the first step is we have to understand what is the base value. To give the base value here, we have to identify what is the chromophore there. So in this case of chromophore, this is carbonyl, this is ene here. So this is my enone here. So this part of the chromophore happens to be member of it's a cyclic system over there. Since it happens to be 6-membered cyclic system, so the base value happens to be 215 nanometer as we discussed earlier. Then we have to look for what are the substituents over there. So we start from here. This is my carbonyl group. So this is my alpha position, this is my beta position. So at beta position there are two things now. This is my ring residue, this is the alkyl substituent over there. So we find that, so one beta alkyl substituent gives me 12 nanometers, that is for this particular substitution over there. And then what we have is one beta ring residue. So this is my beta ring residue at beta position there. So incidentally the two have the same contribution of 12 nanometers each. So we get 12 plus 12, 24 and 215, that gives me a value of 239 nanometers. But rest of the molecule doesn't contribute anything, because we have to keep in mind that we have to talk about the basic chromophore and substituents on that chromophore. So the chromophore ends over here. So these are two substituents that have to be taken into account, and these substituents are not to be bothered about. This part of the molecule is not to be bothered about. Okay. Now we find that the observed value happens to be in agreement with the theoretical value. Okay, let's take yet another example. This is an isomer of the previous system here. What you find is, again the base value is 215 nanometers. Now what you find is, in the previous system we had the substitution here at beta position. Now we got at alpha position. This is very, very significant, because this matters, because if I got alkyl substitution at alpha position, we find that the contribution is 10 nanometers, whereas at for beta position it was 12 nanometers. If it is at gamma position, it is 18 nanometers. So we find that this position of the substitution also matters here. So this gives me 10 nanometers. At beta position now we find that there is a ring residue here. So it will give me 12 nanometers more. So the expected value will be 237. Observed also is 237. Okay, let's take yet another example here. So in this molecule, how do we go about it? Now in this case, what we find is, this is my basic chromophore again. This is my again a cyclic system. The base value will be 215, because it is a 6-membered cyclic system there. And now what you find is, this is my alpha position, this is my carbonyl, this is alpha position. At alpha position we got a ring residue, we got a ring residue at beta position. So there are only two substituents there, alpha ring residue gives me 10 nanometer, beta ring residue gives me 12 nanometer. The 2 add 2 give me 237 again. So there are molecules which are very similar. That's why they are giving me similar lambda max positions over there. Okay, let's move further. Take yet another example here. Okay, this is slightly more involved system now. So how do we go about it? In this case, what we see is that this is my basic chromophore here, this is on, and this is my ene. So this is my enone, and this enone happens to be part of a 6-membered ring. So the base value is 215 nanometers, no problems at all. But now what you see is that this is my chromophore, and we find that this is one extension and this is the second extension. So there is an extension of conjugation. There are 2 steps of this. That means this is extension of conjugation by 2 double bonds. So that is 2 of extension of conjugation, each will contribute about 30 nanometers. So this contributes about 60 nanometers, significant contribution to the chromophore. Now as a consequence of this, now my chromophore starts from here. This was the starting of chromophore, and then with this extension the chromophore extends till here. So this whole thing is my chromophore now. Okay, what do we do next is we look for other contributors. The other contributors we will find is that we got a 1 beta ring residue. So this is my alpha position. At beta position there is a ring residue here. This is part of the ring here. So this gives me 12 nanometers. If I go further, so this is my alpha position, beta, gamma, delta, omega. So beyond delta we find that there is another substitution over there, and further on also epsilon position also there is a substitution here. Now what you find is that in this molecule there is one very significant thing here. We find that okay, this was extension of conjugation. Now these 2 double bonds which have extended my conjugation of the chromophore over here, they actually form a part of a homoannular system. We know that for a homoannular system that contributes again a significant value to the lambda max position, and that happens to be about 39 nanometers, large number here. Then so we have got the chromophore starting from here and moving till here, and then this also has been taken care of. Now we come down to the substituents other than that what we taken care of earlier also. So on this chromophore we find that this is one substitution here, second, and this is my ring residue here. So these are 3 substituents here. Since they go beyond delta, we can put them all together. So we have got 3 alkyl group oblique ring residues, because we find that these 2 are alkyl groups. This is my ring residue here. So each one of them contributes equal of the order of about 18 nanometers. So the total contribution comes out to be 54 nanometers, because all positions beyond delta will give me 18 nanometers. So it comes to 54. And in addition to this, we find that there are 3 double bonds here. Out of these 3 double bonds, this double bond here, this one actually is exocyclic to this ring. So this also will contribute. This will contribute by a value of about 5 nanometers. So if I add them all together, we find the calculated value for this molecule happens to be 385 nanometers. And observed value also is about 388 nanometer, which is in excellent agreement here. So we find that these rules are quite good, because they give a reasonably good value. They give me an opportunity to calculate the predicted value for a given system by using these contributions over there. Okay, let's move further. Let's move further and take yet another example here. Now in this case, how do we go about? Again, we will look for the chromophore first. The chromophore happens to be this and this here. And since this happens to be part of a 6-membered ring, so our base value will be 215 nanometers again. Then what do? Then we look for the substituents here. So we find that at alpha position there is an OH here, at beta position there is an alkyl group, and there is a ring residue here. So there are only 3 substituents here. We will see the contribution. So alpha hydroxy gives me 35 nanometers. It's a large contribution here. And then we find that a beta ring residue gives me 12 nanometers, and a beta alkyl group gives me 12 nanometer again. So these all put together, they give me a value of about 274 nanometers. So that is the kind of value we have for this molecule. The observed value is about 270 nanometers, which is in reasonably good agreement here. Okay, let's move further. take some more example here. Now in this case what you find is that the chromophore happens to be a part of a 5-membered ring. So in this case the base value will be 202, that is 202 nanometers. And if you look at the substituents, we find that at the beta position there is a hydroxy substituent here, and also we got a beta ring residue. If you contribute for them, beta hydroxy will contribute 30 nanometers and the ring residue will contribute 12 nanometers. So they will add together to give me a value of 244 nanometers, and the experimental value happens to be 247, which is fairly good. Okay, now let's move further and look at one more molecule here. I am trying to give you a variety of molecules so that we can understand that how do we use these rules here. In this case what we are going to do is, we have got this molecule, we want to predict calculate this the lambda max for this molecule, but I want to do it in hexane as a solvent system. How do we go about? The basic things remain the same, that is we start by looking at the basic chromophore, and that chromophore happens to be part of a 5-membered cyclic ring, so it is 202 nanometers. Then what do we have is, we have got extension of conjugation, and also we got substituents at beta position, gamma position and delta position. If I just put contribution for that, alkyl group at alpha position, beta position gives me 12 nanometers, extension of conjugation gives me 30 nanometers, a ring residue gives me 18 nanometers. So we are used to this, and then a delta residue gives me 18 nanometers again, and then what do we get is, we got one exocyclic double bond also, we understand that. What's important is that from all this, if we calculate with the value of lambda max for the alcohol as a solvent comes out to be 285 nanometers. But our objective was to find out the value for hexane as a solvent system. So we have to apply the solvent correction there. The solvent correction for hexane happens to be minus 11 nanometers. So what we do is, to get the value in hexane as a solvent system, we find that this is 285 minus 11, the value will be 274 nanometers. So that is how do we apply the solvent correction. That is, if I want to find out a lambda max value for any solvent other than alcohol, then I have to apply solvent correction. Otherwise, if I am using alcohol as a solvent system, then the typical values, the base values and that of the substituents from the tables we can use together to get the value of lambda max. Okay. Now let's sum up what you've done today. What you've done today is, we started by reviewing the contents of the previous sessions, and thereafter we stated the Woodward-Fisher rules for INOs. We started by talking about the basis of it and then stated these rules, and then having done that, we applied these rules to predict the lambda max position for variety of molecules, different classes of molecules, all containing INOs as the basic chromophore over there. Now with this we come to the end of our discussion on UV visible spectroscopy. In the next session we will talk about IR spectroscopy. Thank you.